point out to you that we have a STEM event tomorrow, so that's at 11:30 in the courtyard, and then there'll be a STEM Club meeting after that at 2 o'clock, and everyone's welcome to come by. There'll be some games, activities, a free lunch, and just kind of a chance to get acquainted and have a little bit of fun. So that's tomorrow. Now, I've passed out a couple of things to you that are on that front table. One is our group quiz for today. And so this is something we'll be looking at later on in class. I want to cover some subjects before we get to this. But this is an application of things that we've already covered. But it'll give you an idea of the kinds of questions that you might see on the first quiz and, of course, on the midterm. Also, pass this out. I'll try to give you a couple of challenge problems each week, which are things that aren't necessarily that hard to solve, but maybe you need the right approach, and so you might have to think about it a while to see what the right approach is. These problems are ones, if you are able to knock off the first one pretty fast today, then during our problem-solving session, you could start in on these and ask some questions about that and get going into those as well. What I'm going to try to do, and we'll see how this works, I'm pretty sure there's no class coming in after this one, and so I've scheduled an office half hour for immediately following this class so that we can continue on working with the in-class activities. In order that these are done in a timely manner, I'm going to ask that you finish these up and turn them in today sometime, and I'll set up a little thing so you'll need to scan it and upload it. And so that's the way that all work goes. I thought that there was a little bit of a lack of interest because there wasn't an imminent due date last semester. And so this is the way that I'm going to try to correct that. So this will be worth a couple of points, but more importantly than the number of points that it's worth, it'll give you an idea of the kinds of questions that you can see on the quizzes and exams. And if you've had me before, you know that I'm not trying to trick you. And if you follow through with the kinds of problems that I'm giving you, if I think something's too tough to put on an exam, I'll probably give it to you as an in-class activity or something else first, so that you have a chance to look at it. So that you're not just blown away by something that you've never seen before that's ridiculously hard. That, you know, I know that is sometimes the strategy of some instructors, but I think that this is more straightforward and gives you an opportunity then, if you put in the effort, to do well in the class.
Yeah.
Okay, so again, we'll have a quiz a week from today, and I'm not sure yet what format I'm going to make that, because in some situations it's probably better to get used to a multiple choice format because part of the exam, part of the midterm is multiple choice, but in other cases a free response might be more warranted, depending on the kind of problem that we're dealing with. And so I still have yet to decide how I'm going to structure that first quiz, but it'll either be a free response or multiple choice, or maybe a combination of the two, to give you an idea of how the midterms would look. Okay, so where I want to pick up from last time is to just look quickly at some of the relationships that we derived. And these were very important relationships that are essentially our working relationships for all of the wave motion that we'll be doing in chapters 16, but also 17 too, with just slightly different quantities being defined. We can also use these same principles in chapter 17 and also in our optics and light sections as well. We'll be using these same basic equations. And so one of them that I think is really super important is the velocity of the wave motion is equal to frequency times wavelength. And so this is how fast the energy is being delivered, not to be confused with the transverse velocity, which is the speed of the particles in the medium that are transmitting the disturbance. Okay, and so how do we know what the velocity is? Well, typically, the velocity we can think of as being a product of two different things. Or in this case, a quotient, I should say, of two different things. In general, the velocity is equal to an elastic factor divided by an inertia factor. So the elastic factor deals with the restoring force that tries to drive the system back toward equilibrium. And so if we're talking about, say, the tension in a string, the elastic factor would be how tightly the string is pulled. And so it's directly proportional to that elastic factor. So you can see this here, although I do this with a compression wave, you can see how this would work with a compression wave. If I've got very little elasticity, it means I haven't pulled it very tight. So look how fast the wave energy is traveling. Not much of an elastic factor here. But now, look what happens if I stretch it out. You can see how much faster the wave energy is being transmitted from one place to another. And so that elastic factor can take on many different forms depending on the type of wave that we're dealing with. That in the case of a string wave, it would just be the tension in the string. Then that's divided by an inertia factor. And that inertia factor relates to how much mass there is that is being moved back and forth with simple harmonic motion. And so in the case of a string, this would just be the mass per unit length of the string. So we could, for string waves, which is kind of a classic way to start out transverse waves, we can say that the velocity is equal to the square root of the tension in the string divided by the mass per unit length. Now, some people call that T. I don't like calling it T because we also have period. And so I'm trying to keep from reusing symbols in a confusing way. And then mu is our mass per unit length. So we can think of this as being the mass density of the string. For example, if we had a string that had a length of 10 meters and a mass of 1 kilogram, then mu would be equal to 0.1 kilograms per meter, be the mass divided by the length. And so that's something that we'll be doing in lab. Now, a reminder, there's no lab this week. We're not to the point yet where we've even begun sound waves. And we're just going to get started with standing waves that are transverse in a string today. So we're going to wait to do our first lab until next week. That will get the essentials going this week. And some of the things that you will need for the lab will be covered today in class. Okay, so this would be the situation then for this kind of a string. And then let's say that the tension for this problem was equal to 10 newtons. Then we could calculate the velocity as the square root of 10 newtons divided by 0.1 kilograms per meter. That would give us the square root of 100, or 10 meters per second. So that's how fast the wave energy would be delivered from one location to another. Now, later on, I'm going to derive why this is the right relationship, why this is the correct elastic divided by the inertia factor. That involves using what we call the wave equation and F equals ma. So this can all be derived from the wave equation, F equals ma, and I'll have a handout on that I'll pass out next time that'll help to explain some of those things in more detail. But that is covered in your textbook as well. Okay, so this is one of the important things, and we need to be able to know what the velocity is, and it's important to realize here that it's a function of the properties of the medium. But as long as the properties of the medium remain constant, then the velocity stays the same. So as long as we don't change the tension or the mass gradient of length, as the frequency goes up, the wavelength goes down. So let's say we start out with a wave like this that has a frequency that's equal to 100 hertz. We have a velocity of 10 meters per second and a mass gradient length of 0.1 kilograms per meter. And so from this, then, we should be able to figure out the wavelength. The wavelength for this would be just one equation and one unknown. We have the velocity now. We just calculated that. So the wavelength then would be equal to what? It would be the velocity divided by the frequency. So that would be 10 meters per second divided by 100 hertz. So that would be equal to 0.1 meters. Or that would be the same thing as a 10 centimeter wavelength. Now, let's say that we increase the frequency. So how do I do that? Well, I'm just sitting here vibrating this thing. If I do it at 100 cycles per second, I'll send waves through that have a wavelength of 0.1 meters. But what if I increase that, say, by a factor of 10? What if I say now, increase the frequency to 1,000 hertz? Let's find the new wavelength. So we'll call this F prime. 1,000, and let's find lambda prime. So now our lambda prime is going to be equal to the velocity. But remember, that hasn't changed. Just because we've changed the rate at which we're shaping the medium, that's not changing the velocity. But it is changing, of course, the frequency. And so then this is going to be 10 meters per second divided by 1,000 hertz. And so that would be just 0.01 meters, or 1 centimeter. Okay, so this is 10 centimeters, but by increasing the frequency by a factor of 10, now the wavelength is 1 centimeter. Okay, so how can we explain that? Well, I think the easiest way to think about that is that if you're vibrating faster, you're adding more energy into the system. If you add more energy into the system, that means that if that energy can only travel at a certain speed through the medium, then it's going to have to squeeze the waves up so that you get more waves into that same length. Okay? And so by squeezing more energy into the system, we automatically then shorten the wavelength by increasing the frequency. And you notice here that they're proportional. I increased the frequency by a factor of 10, then the wavelength dropped by a factor of 10. And so that's the kind of compensation that we can expect as long as the velocity of the waves traveling through the medium remains constant. Are there any questions about that? Okay, we also had an expression that was a function of two variables last time. And it looked something like y is equal to a times the sine of kx minus omega t plus phi. And so we looked a lot at that, and we also looked at the idea of the transverse velocity, bt, is equal to, what was that, minus omega a times the cosine of kx minus omega t plus phi. And we got the tangential acceleration, which is minus omega squared a sine kx minus omega t plus phi. And that was equal to minus omega squared y. By comparing this with that, we see that the acceleration can be written strictly in terms of the displacement. And this is really an expression of Hooke's law. This is really another way of writing Hooke's law, F equals kx. And so you're not always going to see it, though, in that form. We saw before that the wave velocity, v, wasn't just equal to frequency times wavelength, but it was also equal to omega over k, where k, if you'll recall, 2 pi over lambda, and omega is 2 pi times the frequency, or equivalently 2 pi over the period, because the frequency is 1 over the period. So those were kind of consolidated results from last time. Okay. The thing here to keep in mind is that when it's a minus in there, it's motion to the right. When it's a plus, it's motion to the left. And if we have something that looks like the sine of omega t minus kx plus omega t, that's motion in the negative x direction. Why is that? Well, again, if we write an expression for what would happen if we keep the phase constant. And so to follow with the wave, in the top situation, we have kx minus omega t is equal to a constant. And here I'm not using the phase angle in there, but we very quickly will be using the phase angle. But it doesn't matter whether you have the phase angle in there or not. We just include it for completeness. But when we implicitly differentiate, and we did this last time, k dx minus omega dt is 0, gives us dx dt is equal to omega over k. So as long as the wave velocity is equal to omega over k, we're following along with the wave at constant phase. So we're staying here on the wave, and we're staying right with the wave shape, because we're moving right along with it. But what about in this situation? Well, here we'd have kx plus omega t plus some arbitrary phase angle would have to be a constant. So if we implicitly differentiate that, we would get k dx plus omega dt equals 0. Or this would give us dx dt is equal to minus omega over k. So when we add the omega t instead of subtracting it, that's motion in the negative x direction. Because to keep the argument constant, as x gets smaller, x is getting more negative, and t is getting more positive, That's the only way that we can maintain a constant value for the argument of the sine function. And that's what we have to do to ride along with the wave. We've got to keep the argument of the sine function constant. And that requires that we move with the wave velocity either to the right or to the left. So when you see this plus sign there, it tells you the waves are moving in the negative x direction. When you see the minus sign in there, it automatically tells you they're moving in the positive direction. But sometimes, and it depends on the textbook that you're using, they'll use this expression. First of all, let's see how the phase angle can turn a sine function into a cosine function. Okay, let's say we've got something that looks like this. And we've got another function that looks like this. It starts out, then it goes to 0 here, then it goes to maximum negative there. Then it goes back to 0 here, then back to maximum positive there, etc. So we could write this then as the sine, let's say, of kx minus omega t. We could say, well, this wave is moving along. But what if we've got that wave? That looks more like a cosine function. So we might think of this then as being the cosine of kx minus omega t. So that would just be different from this function, assuming the amplitudes were all the same, and the wavelengths were all the same, everything else matched up. This would just be this function shifted by a 90-degree phase angle. Okay, so if you move this through a quarter of a cycle, then you've got this. Okay, and so we could just as easily write this function and this function as being sine functions, but with a different phase angle. So that's the key thing here. And so how do we do that? Well, let's look at a simpler function first. Let's look at something like y equals x. And then if we want to shift that to the right, let's say we want to shift it to the right by 1 unit. Are we going to add 1 to the x or subtract 1 from the x? If we add it, then when x equals minus 1, what is y? 0. So that's not going to work. That's going to give us this function, isn't it? To get this function, we have to subtract 1 away from it. Then, when x equals 1, y equals 0. Okay, so a shift to the right corresponds to subtracting something from the horizontal coordinate, not adding. Okay, so that's an important point. And so here then, if I want to shift this thing to the right, then that's going to be a phase shift, essentially, of 90 degrees, or pi over 2 radians. Okay, so go ahead and write this expression with the correct phase angle. Go ahead and just do that right now. This is equal to the sine, in other words, of kx minus omega t plus phi. Tell me what phi is. Just follow the model over there with y equals x and y equals x minus 1. Is the phase angle going to be positive or negative? Negative, good. Why is it going to be negative? Because we're shifting to the right. So that's what we did here. When we shifted to the right, we subtracted something, right? So that's what we're doing here. We're shifting to the right, so we're subtracting something, and so phi is then what? Minus pi over 2. Good. Okay, so now we've written both of these essentially as having the same sinusoidal dependence, same functional dependence, assuming the amplitude is the same, we can put that in there too. The only thing that's changed is our phase angle. So in this case, we also have a phase angle, but it's 0. And so that means that you can change a sine function into a cosine function anytime you want, just by adding the appropriate phase angle. And so in this particular class, then, we're more interested in following through with the way that's written in the book, just because that doesn't mean that I couldn't give you a different problem, one that involves a cosine function, and ask you to write it in this form. Or here's another variation on this. Let's say we have something that looks like a times the sine of omega t minus kx. Could we write that in the form a times the sine of kx minus omega t? Well, we could if we multiply what's in here by -1. So we could say here that this is a times the sine of -1 times kx minus omega t. Okay. But does anybody know what the sine of minus theta is equal to?
It's just cosine theta.
Here's theta. This is y over z. This would be x. This would be minus theta. Y over z. So the y and the z are the same, but isn't it negative? Yeah. So the sine of minus theta, this is one of your trig identities, but it's something you can figure out in your head if you don't remember it. Minus the sine of theta. So we use that here. We just see that this is equal to minus a times the sine of kx minus omega t. And so it's a negative sine function. Does everybody see that? So if we have a positive sine function, looks like this. This is our negative sine function. So can we write this as a positive sine function that's phase shifted? Yes, we can. How much do we need to shift this by so that it looks like a positive sine function? Pi. Either pi or minus pi. And so sometimes that gets tricky. Which way do you go with it? It depends on the initial conditions of the problem. That either one would be correct if all that we're trying to do is find the correspondence between these. So we could rewrite this then as the sine of kx minus omega t plus or minus pi. And then we decide which one of these we want depending on other initial conditions that were given in the problem. But can you see that this expression is equivalent to this expression, but just for the shifted phase angle? That's the important point here. And so we can turn something that's an omega t minus kx into a sine of kx minus omega t just by shifting the phase angle. We can do the same thing with the cosine function, because the cosine function is just the sine function we already saw over here, shifted by 90 degrees. And so anything that looks like the sine of omega t minus kx, or the cosine of omega t minus kx, plus some other phase angle, phi 2 plus phi 1, whatever these phase angles are, those are all equivalent then to sine of kx minus omega t plus phi 3. Every single one of them. And so if this is plus, then all that does is that changes the direction of the wave. Okay, so you could just as easily have a cosine of omega t plus kx or a sine of omega t plus kx, and those would both be waves that are moving in the negative direction, using the same argument that we did before, where you implicitly differentiate the inside and hold it constant. And so there's nothing magical about this particular form. It can take on all of these other variations of sine and cosine with just the appropriate adjustment of the phase angle. Are there any questions about that? Okay, so don't be surprised and don't freak out if I give you something on a quiz, looks like the cosine of omega t minus kx, and ask you to find the wave velocity. If that, you don't even need to worry about what the phase angle is, right? You just know that the velocity is still omega over k. It's still the same thing. It's just written with a different phase angle. It looks a lot different, but it's the same. It represents the same thing with a different phase angle. All right, so the next thing that I wanted to look at, in a little bit of detail, is, well, we said before that waves generate energy, and the energy is delivered from one place to another. And so if that's the case, then we might be interested then in how much energy is being delivered. So there are different ways of deriving this expression. I'm going to use one of the simpler ways that brushes a couple of technical details under the carpet, but I think it's the easiest one to understand. That's why I'm using it. So let's say that we've got a little element of mass here, delta m. And we have a wave that is moving with a wave velocity v to the right. And I want to figure out how much power is being delivered. And so that means that over here, I have some receiver. Could be a bob moving up and down, or I might be delivering this energy to a mass which is experiencing work as it moves up and down. Or this could be a compression wave. And if it's a compression wave, then these would just be variations in pressure. For a compression wave, then that energy would be delivered, say, into vibrating your eardrum back and forth at a certain rate. And so whatever mode this energy is being delivered, we can talk about the rate at which it's being delivered. And so that's an important thing, because that's what waves do, is deliver energy. So if we look at the total energy of this simple harmonic oscillator, remember every point in the medium can be thought of as a simple harmonic oscillator. But each one is just a little out of phase with the one that's next to it. And that's what causes the wave to perpetuate along. This one pulls that one up, then that one pulls this one up, and then that one pulls this one up. And so they're all simple harmonic oscillators moving at the same frequency, but they're just a little out of phase from each other. So let's just look at one of those little elements, and we can call that mu delta x, where delta x is a small length of the string. We could call it dx if we wanted, but here I'm just going to call it delta x. And so the energy then of that mass element is equal to 1/2 k a squared, where k here is our Coulomb constant and not our wave, I'm sorry, not a Coulomb constant, our spring constant, not our wave number. Put a little feed on it so that we don't confuse that with wave number. That's our spring constant. And what we learned before in Physics 208A is that the frequency of a simple harmonic oscillator goes like the square root of k over m. So in this case, we'll look at that m as being that little element of mass on the string. Okay, and so this was the frequency of any simple harmonic oscillator where we have a spring constant k so that it'll oscillate back and forth with an angular frequency that's equal to the square root of k over m. So that means that we can rewrite the k here as delta m times omega squared, which is what I'm going to do here. So this is going to be 1/2 times delta m times omega squared a squared. And then I'm going to look at the rate at which this energy is being delivered. And so that's going to be dE dt. Remember, the derivative of the rate of energy, that's in, what, joules per second, that's watts. We'll do a lot more with that in this class than we did last semester. So you want to be real clear as to what that represents. That's power. In this case, the average power delivered over a cycle. And so that's going to be d by dt of 1/2. And then here, I'm going to write in for delta m mu delta x times omega squared a squared. So essentially then, the only thing that's changing in here is the delta x, because this delta x is moving to there as the energy is perpetuated along. Then that delta x moves to there, and then that delta x moves to there. So you can rewrite this then as 1/2 mu times dx dt, or delta x delta t. If I made this a dx, then this would be dx dt. That's our wave velocity times omega squared a squared. Let me just write that up here because I know I got too low. Careful. Power then is equal to 1/2 mu v omega squared a squared. Now there's some interesting aspects to this. One thing that we should note is that the energy and the power are proportional to the amplitude squared. And that's something that we're going to see in any kind of wave motion that we're dealing with. Is, let's say you turn up the amplitude of the sound on your radio, and you double the amplitude. Then you're quadrupling the power. So doubling the amplitude is going to make it sound 4 times louder, assuming that your ears pick up all the frequencies the same, which they don't. But if you assume that, the power is proportional to the amplitude squared. And so if we already know what the velocity is, then this is a useful form. If v is given. But if v isn't given and the tension is given, then what we would want to do is eliminate the velocity in favor of the tension by writing it as the tension per divided by the mass per unit length, square root. So this is an equivalent form. One half mu. Then here I'm going to put the square root of the tension divided by the mass per unit length, like that, times omega squared a squared. So a lot of times, that's what we're going to know. We're going to be able to measure the tension in a string, let's say. Maybe a little easier than we're going to know what the wave velocity is, although we could do a separate calculation to get the wave velocity, and then use that top form. Now, you can think of this as the, if we bring the mu inside of here, then that's the square root of mu squared. So if I do that, then one of the mu's will cancel inside of the square root, and that'll give me 1/2 square root of f mu times omega squared a squared. So that's another form for equivalent power. Any questions about that expression before we actually crunch out a number? You notice again that it's proportional to the amplitude squared. So here's our problem. We have a piano wire with a mass of 4 grams and a length of 0.8 meters that's stretched to a tension of 30 newtons. And then we send waves with a frequency of 60 hertz and amplitude of 1.5 millimeter along the wire. And then we'll calculate the average power. Okay, so let's just picture this. We've got a piano wire, 0.8 meters, 80 centimeters long, has a mass of 4 grams. So it's a pretty light string. But, and so it's not hard to get the mu value for this, but you want to be really careful that you don't mess up your units. Okay, so we want the mass to be in kilograms. So don't always assume, because a lot of times you'll see the problem given in the right units, that it's always in the right units. So our mu then in this case is equal to the mass, so that's, what do we got here? 4 times 10 to the minus 3 kilograms divided by the total length, which is 0.8 meters. So that's what I've got in here for mu. And so that would be a big source of error I found just from grading Physics 208A exams. It's not changing the units, thinking automatically, going to the next step, just taking those numbers and plugging them in and not thinking, am I in meter, kilograms, seconds, units? This is not a hard problem to do as long as you get the units right. Then newtons, that's fine, so we're good to go there. And then this shouldn't be there because it's just the square root of mu f. And so then omega, though, is 2 pi times the frequency. Okay? And so that has to be squared. So the frequency was given, but omega wasn't given. So there yet is another unit conversion. You have to convert from cycles per second to radians per second, knowing that omega is 2 pi times the frequency. Then we square that. Then we have to multiply that by the amplitude squared, and the amplitude's given in millimeters. So you see here that this is just a plug and chug one-step problem, but you have 3 different steps to make sure the units are correct. And so that's what you want to be really clear about here, is that you're in the right set of units. And so this millimeters, that's 1.5 times 10 to the minus 3 meters. So we crunch that number out, we get 0.0619 watts. Okay, so that's 6/100ths of a joule per second. Okay? 0.0619, 0.062 essentially, joules per second of energy are being delivered from one end of the wire to the other. Now what happens if we double the amplitude? Well, we don't have to go all the way through. We just know that doubling the amplitude here is going to quadruple the power, because you're going to have, instead of a squared, you'll have 2a squared. So that's going to be 4a squared. So that's what tells us the power is 4 times higher when we double the amplitude. And so that's that critical thing that I talked about before, with power and energy being proportional to the amplitude squared. Okay, so are there any questions about applying what we've talked about so far to power? Yes?
Could you explain one more time the difference between the two bottom of the?
Which two
Oh,
bottom?
on the board. That's written on the board under the note.
This here, we bring it inside, it's mu squared. Mu squared over mu is mu.
Okay.
So I just brought it inside of the square root, and then I consolidated within the
Oh,
square
yeah.
root.
Okay. Thanks.
Any other questions? All right. So that brings us then to interference of waves. We've so far just been talking about a single wave. And here, this is another picture of that thing I showed you before, where if the frequency goes up, the wavelength goes down. That's all this is meant to show here. And so that means you're bobbing up and down more times per second, but you're squeezing more energy into the same length of the medium. And then here, this is just another illustration of the idea that as the wave moves this way, the particles are doing simple harmonic motion this way. So this particle then pulls up on that one, and then when this one gets to there, it's at this point, and then this one pulls up on that one, so by the time this one gets to there, it's at that point. And so it's a chain reaction of just kind of dragging the next one along that's slightly out of phase with the one that was in front of it. That is allowing this wave energy to be transmitted at a certain velocity. But the actual particles, if you think about it mathematically, it's essentially an infinite collection of simple harmonic oscillators that are slightly out of phase with each other. It's not really infinity, because you can eventually break these down to atoms that are moving up and down, but it's a very small length here that is associated with each simple harmonic oscillation. Okay, so next, let's look at interference of waves. Now, when waves add together, there's a very simple rule for how they interfere. By interfere, I just mean they overlap with each other. They move through each other. They could be moving in opposite directions, or one could be moving in the same direction as the other, and they could be interfering while they're moving in the same direction. Our basic rule then is that the amplitudes of the waves always add, or subtract if they're negative, that you're adding a negative if they're negative amplitudes. But the amplitudes add in the region of overlap. Okay, and so we've all been in this situation before, say, where you've been in a bathtub of water. And then you're just kind of messing around, and so you start pushing up and down on the surface of the water. You ever done that? And then the waves start getting bigger and bigger, and all of a sudden it starts slurping out over the whole floor, flooding everything, and then what do? Instinctively, you start adding in out-of-phase waves to cancel out that out-of-control wave energy. And so in one case, you have what's called constructive interference, where the waves add. In the other case, you have destructive interference, where the waves cancel. Now, often, this is related to what we call resonance. Doesn't have to be. That constructive interference happens when the waveforms make the composite waveform gets bigger. And in destructive interference, or this cancellation process, we have the composite waveform get smaller. So there are examples of when you would want constructive interference. Let's say you're trying to amplify a sound on, that is a vibration of air, say, on your guitar string. And so you use an amplifier to boost that sound level. Okay? And so you can take, and by adding energy to the system, you can make the amplitude of that wave get bigger. And so that would be an example of constructive interference. But if you wanted to soundproof a room, then that might be an example of destructive interference. Let's say you have, you go out on a camping trip, and everything's so nice. You're just sitting out there, relaxing, listening to the gentle sounds of the birds, and you hear a little bit of stream flowing in the background. And then this family with a big camper pulls into the campsite next to you and turns on their generator. And so, it's just kind of disrupting. And so, very calmly and politely, you go over and you say, well, would you mind digging a hole, putting your generator in the hole, and then covering it up with plywood, and then putting a bunch of dirt on top? He goes, oh, sure, I'd be glad to do that. Okay. And then that solves the problem, because then the waves inside of that trapped space are going to bounce around in a random way so that they get out of phase with each other, and they tend to cancel. And so, problem solved. Okay. And then you can have combinations of constructive and destructive interference, where sometimes the waveform gets bigger, but at other times it gets smaller. Okay, so here, if we had two identical waves, then this wave and this wave would add up to the amplitude of the composite wave. But here, this wave and that wave would have amplitudes that are the additive inverse of each other, and so they would add to 0. And so if you have destructive interference then, where do you suppose the energy goes?
It's still there.
It's still there in what form? Let's say you had a square wave moving along like this, and another square wave moving along like that. And they're moving toward each other. They get into the region of overlap. Let's say they're here. And then what we're going to get for the composite wave, something looks like this. Then in here, it's going to go to 0. And then here it's going to go down like that. And so that's what it's going to look like when they're partially overlapping. But then a short time later, it's going to look like this. So we know there's power being delivered. We go, well, it's a negative amplitude. But no, the power goes like the amplitude squared. So even if it's a negative amplitude, you haven't gotten rid of the power. I haven't canceled the power out. The energy's still there. But that's what your composite waveform looks like. And so what's happening here that is basically a different form of energy than what's happening here? What perpetuates the disturbance? Isn't it the particles in the medium? So we looked before at how the energy of the particle in the medium, moving up and down, could be delivered from left to right. But in this case, what's happening is that the amplitude has to change so fast. Here it would actually be changing infinitely fast if they were perfectly square waves. But if there was a little bit of a slope to it, there'd be a tremendous change in the velocity of the transverse particles in the medium. And so it's stored as essentially the energy of the particles in the medium as they move very quickly toward equilibrium. So the energy isn't destroyed, it just kind of looks like it is.
So, a few seconds after this, folding.
Right, and then if you keep going, then they just continue on their merry way as if nothing had happened. They have their original form, they're good to go, and it's as if there had never been an interaction once they're outside the region of overlap. Any other questions about that? Okay, so there are, okay, so here's an example then of the constructive interference of similar waves moving in opposite directions. We can see that when these two waveforms here they're close to each other, but not completely overlapping. And then here they're completely overlapping. Here's an example of where their amplitudes are oriented in the reverse manner to each other. So this we could think of essentially as being a phase shift of the incident wave, if this were a reflected wave. And then at this moment, it looks like the wave energy isn't there, but it's actually stored in the energy of the particles that are moving really fast to get to that point. And so the energy is still there. Okay, now, you can have what are called standing waves. And this is an example of constructive interference, which is a particularly useful one for all kinds of different applications. This is the basic equation for resonance. And it turns out even particles of matter can be thought of as being standing wave patterns, if you think about it in the right way. So when we pluck a guitar string, you hear sound. That's a particular sound that is actually a standing wave pattern. Okay, and so let's go back. We can have a glass. You may have seen this before on an old Memorex commercial where the sound energy comes in and starts vibrating the glass. And then the glass shatters. And so what's happening? Well, essentially, what you do is you have some kind of a disturbance here that moves the medium up and down. And then what you get are waves that travel around in both directions. So some of the wave energy goes this way, but some of the wave energy goes this way. And for certain specific wavelengths of the vibration, if you can match the natural frequency of vibration of the glass, so you turn the frequency up higher and higher until finally it breaks, then at that point you develop standing waves. And those standing waves are constructively interfering. And so this is our general definition for standing waves. It's a constructive interference of similar waves that move in opposite directions. Okay, and so in this case, you've got a wave moving this way, you've got a wave moving that way, they meet, and they constructively interfere somehow. But in the process of doing that, they generate something that appears to be standing still. So the wave looks like it's standing still. But they're actually the constructive interference of two similar waves moving in opposite directions. It doesn't have to be two, it could be more than two, but in this case it would be two. And so when you ring a bell, that's a standing wave pattern too. That's just like this. Basically what you have when you hit the bell is you've got waves that will tend to move through. A lot of them will destructively interfere. But the pattern will remain the same. So you'll have nodes here. These would be points of zero displacement in the median, and they stay put. They don't go anywhere. These are nodes. And then these points of maximum displacement are called antinodes. And this is what stresses the material. And when it exceeds the elastic limits of how much these adjacent antinodes are accelerating the material, then you start getting cracks in this thing if it's a glass. Or with a bell, eventually, I guess, you would melt the bell if you added too much energy to the system during one cycle. This also is the same phenomenon that happened during that Alaska earthquake that I showed you some pictures. Remember the devastation of that last time? That was the second largest earthquake in history, and it released more energy than all of the other earthquakes in the 20th century. And so there the earth was being sent ringing like a bell in the same kind of a vibrational pattern. We also see this kind of circular vibrational pattern with electrons. Using what we call the Bohr model for the atom, you could actually think of the electron as being a traveling wave that is moving around the orbital nucleus in both directions, and then constructively interfering with itself. So we get to quantum physics in 208C, those of you that decide to take that. We'll be looking at the standing wave patterns and how that relates to matter having specific wavelengths, frequencies that it gives off, why matter tends to be stable in the ground state, because according to the principles of physics, it should keep releasing electromagnetic waves, and the electron should spiral into the nucleus, but it doesn't, because there's a basic standing wave pattern. You get smaller than that, then you just get destructive interference. So you have to think of the electrons as being waves in order to understand these basic properties of the atom. Okay, so those are things that we'll get to later. But one of the simpler ways to look at this is just with a standing rope wave. And so that's what we're going to be spending a lot of time with here, is this model. And then this model is going to have a lot of applications, surprisingly, to other systems, but is very much involved with music theory. That's just one of so many applications that I can't even think of what they all are right now that have to do with resonance and standing wave patterns. Okay, and so here's a rope standing wave then, and it's actually a constructive interference of two similar waves that are moving in opposite directions. And they interfere in the middle to produce this kind of a standing wave pattern. Okay, so I'd like to illustrate that here on the floor. Could I have a volunteer to hold the other end of the slinky for me? Okay, great. Okay, you might want to stand up for this, because this is really worth it, I guarantee you. Okay, go ahead and hold it on the ground, and just hold your end solid. Okay, so first of all, I want to illustrate what happens if I just send a single wave pulse through. Notice what happens, and I need to put a little more tension in this, because we have damping on the floor. Okay, so I'm going to send a wave through. Notice that I get a reflected wave coming back. The reflected wave is 180 degrees out of phase with the incident wave. I send it in up, it comes back down. But now look what happens if I start to add waves. Now if I do it at the wrong frequency, they kind of cancel out. But if I can get it at the right frequency, I can get what looks like a standing wave. Okay, so this would be the fundamental frequency. Okay, so this is like what a guitar string likes to vibrate in, because it's the lowest energy state for the system. Looks like it's a wave that's standing still. You could use a strobe camera to look at a picture of the wave at, say, this moment, and then one period later at that moment, one period later that moment again, and it would just look like it's a frozen wave. But the important thing here is that the shape of the wave may change its amplitude, but the position of the nodes remains constant. Now I'm going to change the frequency a little bit and try to get a first harmonic. Okay, so this is the first harmonic frequency, and essentially I've doubled the frequency from before. That's cut the wavelength in half. But the important thing here is that as I add more energy to the system, the amplitude gets bigger. If I can overcome the friction force on the carpet, I can make this thing start hitting the walls. Or I can bend the slinky so much that it becomes unusable for anybody else later on. I can go to the second overtone. This is called the third harmonic. And so in each case, we had, here's fundamental. This is the n equals 1 harmonic. This is the first overtone, or the second harmonic. This is the third harmonic. This is the fourth harmonic. And eventually, I need a little more coffee to drink to have enough energy to overcome friction. Thank you. Okay, so, but if I didn't have dissipative forces acting, I could continue to add more and more half wavelengths, and those would all be resonant frequencies for this standing wave. So, what are our necessary conditions? Well, these are sometimes called boundary conditions. And so the boundary conditions are just, that's just a fancy way of saying what's happening at the ends of the system, where the system is bounded. And so to get a standing transverse wave, the end of the string, both sides has to be a node. Remember, a node is a region of zero displacement on the wave. If this condition is not satisfied, then we get destructive interference, and you saw that that was kind of happening, at least a little bit, when I didn't have the right frequency. It looks like it was kind of canceling out. But when I was able to add the right frequency in, then I was exciting one of these resonant conditions. These harmonic waves have nodes at the endpoints, and so therefore we can model them as sine waves. And so we've already got our sine wave expression for the amplitude. So basically then, what we do is we would say we have a wave traveling this way. We could say this is our y1 wave. And then on the boundary here, we have our y2 wave, which would be a harmonic wave that's phase shifted by 180 degrees and is moving in the opposite direction. So you can write y1 plus y2 is equal to a, and let's assume the amplitude stays the same on reflection, sine of kx minus omega t plus the sine of kx plus omega t, like that. And then we can use a trig identity, sine of a plus b is equal to cosine a sine b plus sine a cosine b. And I don't memorize this. All I have remembered is I know the sine of 2 theta is equal to 2 sine theta cosine theta. So I say, okay, well, if A and B are the same, then this would be cosine A sine B. This would be sine A cosine B. But if A and B are the same, then that would just be 2 times the cosine theta times the sine of theta, and this would be the sine of 2 theta. So, that's helpful, because you can just look this up if you want. But when you plug in these values for A and B, what you get is that our amplitude y is equal to 2a times the sine of kx times the cosine of omega t. So it's a product function, even though in here the x's and the t's are part of the arguments of the two sine functions. You can separate them out. And so this then is your basic waveform here. And then this is the modulation of that waveform. The cosine omega t is the time-dependent sign. Okay, and so that means that when omega t here equals pi, then it's down here. When omega t equals 0 or 2 pi, it's back up here. So it modulates back and forth with this term, but this term gives us the basic shape of the wave.